The deep ocean is a vast medium defined by extreme density, creating a highly conductive environment for acoustic waves. Living within this column is the sperm whale, a predator that utilizes one of the most powerful biological sound generators in nature. To hunt in the darkness, it emits an echolocation click with a back-calculated source level of 230 decibels. On land, a jet engine at takeoff registers roughly 140 decibels. A measurement of 230 decibels suggests a level of force that should be physically impossible for an animal to produce or survive. At the surface, naval operations utilize mid-frequency anti-submarine warfare sonar to track submerged targets. This sonar system is designed to produce a peak pressure level that matches the whale exactly, 230 decibels. This identical measurement has led to a common deduction in environmental policy, that if a whale produces a 230 decibel sound safely, then a human-made sound at the same level should be equally harmless. However, there is a documented correlation between these naval sonar transmissions and the mass stranding of beaked whales. This suggests that peak pressure measurements provide an incomplete picture of how sound interacts with marine life. Reconciling the safety of the whale's click with the lethality of the sonar requires an examination of how acoustic measurement changes as it moves from air into the ocean. A decibel is not a fixed unit of weight or distance. It is a relative logarithmic ratio used to compare the intensity of a sound to a specific reference. Because it is a ratio, a decibel count is only meaningful when the reference pressure for the medium is defined. In air, the standard reference pressure is 20 micropascals, the approximate limit of human hearing. In water, where our ears are inefficient, researchers use a reference of just 1 micropascal. As the highlight shows, shifting the mathematical baseline from 20 micropascals to 1 creates an immediate numerical increase of 26 decibels. Beyond the math, we have to account for a physical variable, acoustic impedance. Water is 800 times denser than air. This higher density allows sound to propagate with far greater efficiency. This density difference dictates that an identical amount of physical pressure will be measured as 36 decibels higher on a hydrophone than it would be on a microphone in air. When we combine the baseline shift and the impedance factor, we find a total correction of 62 decibels between air and water. Applying this 62 decibel correction to a 230 decibel sonar ping reveals that it is equivalent to a 168 decibel sound in air. Quoting raw underwater decibels without this correction makes it impossible to accurately assess the impact on a listener accustomed to terrestrial physics. An acoustic measurement is essentially a variable until both the reference pressure and the impedance of the medium are calculated. If 168 decibels is still intense enough to cause damage, we have to ask why the sperm whale is not injured by its own output. The whale utilizes a physiological defense mechanism. It can contract specific muscles to stiffen the middle ear bones, attenuating the vibration before it reaches the inner ear. Anatomically, the whale's skull is shaped to project sound forward in a highly directional, narrow beam, which directs the pressure away from its own auditory system. But the most important factor in this comparison is the time domain, how long that pressure is sustained. This chart allows us to look past peak pressure and calculate the total energy of a sound wave. A sperm whale's click is an instantaneous spike. It reaches its peak pressure and disappears in just 1/10,000th of a second. A sonar ping reaches the same peak, but it sustains its output for over a full second, 10,000 times longer than the whale's click. Tissues are affected by the total energy of a pulse, which is represented by the area under the curve on this graph. While the pressures are the same, the sonar pulse delivers 10,000 times more total acoustic energy to the water than the whale. Furthermore, sonar is emitted in broad horizontal layers, meaning this energy propagates across a massive volume of the ocean with minimal loss. The whale's beam is narrow and attenuates rapidly, affecting only a small portion of the water column. Trauma is a result of the sustained energy absorbed by the environment, not a microsecond of peak pressure. When that sustained energy enters the body of a marine mammal, the physics of the water column translate into physiological damage. Most assumptions about sonar damage focus on ruptured eardrums, but necropsies of stranded whales often show that their auditory systems are intact. The actual pathology found in these animals is a system-wide presence of gas bubble lesions and fat embolisms. This damage is physically identical to decompression sickness, or the bends, which occurs when dissolved gases form bubbles in the blood and tissue. Deep-diving mammals naturally have tissues that are highly supersaturated with nitrogen. Research published by Tal et al. In the Journal of Neurophysiology provides a link between underwater sound and the onset of the sickness. The experiment subjected rats to a controlled, simulated hyperbaric dive profile. While under pressure, one group was exposed to an intense 204 decibel sound field. The rats exposed to sound suffered significantly higher rates of decompression sickness and neurological damage than the control group. This trauma is caused by a biophysical process called rectified diffusion. Inside a whale's supersaturated tissue are microscopic, dormant bubbles of nitrogen gas. The sustained energy of a sonar pulse forces these tiny bubbles to oscillate. During this oscillation, the bubble absorbs more nitrogen from the surrounding tissue during its expansion than it releases during contraction. The result is a bubble that grows rapidly, eventually blocking blood vessels and starving tissues of oxygen. Sonar doesn't kill through blunt force. It triggers a physical reaction that expands nitrogen bubbles until they destroy the animal's internal systems. The comparison between a 230 decibel whale and a 230 decibel sonar pulse is a failure of measurement. While the peak pressure is identical, these two sources differ in duration, directionality, and total energy absorption. The whale click is a low-energy, transient signal directed in a narrow beam. The sonar pulse is a massive energy, omnidirectional transmission sustained over a long duration. Current regulations often define acoustic safety zones based solely on peak source level thresholds. Effective policy requires a shift toward calculating the total energy output, the area under the curve, by factoring in pulse duration. These standards must also be adjusted for the physiological context of the species, accounting for their dive behavior and nitrogen levels. We are introducing sustained acoustic energy into a deep ocean environment where marine life is physiologically vulnerable to it. Protecting marine ecology depends on applying the correct biophysics to our regulatory models. Until we regulate total acoustic energy rather than just peak pressure, our metrics will fail to predict the true impact of sound in the sea.